Okay, everyone, we're still looking at the review chapter, and now we're in section 5 talking about rational expressions. So, a rational expression is the quotient of two different polynomials, p and q, where q is not equal to 0, and that's just because we cannot divide by 0. So, we've been presented with some examples and different forms of polynomials made into fractions. So, you can see we could have something simple like x plus 2. Or in the second example, the factored out form of a larger polynomial, x plus 2 and x plus 4. And of course, the last one, which shows the multiplied out form of the polynomials, 2p squared plus 7p minus 4, and on denominator side, 5p squared plus 20p. So all of these are valid ways to uh, write a rational expression, as long as you have two different polynomials that are making up the numerator and denominator. Now, these are referred to as rationals. A rational expression has a very specific domain. It's the first function we talk about when we think of domains that are restricted, specifically because the denominator of a rational is never going to be equal to 0. Because if it was, we would be dividing by 0, and that, of course, presents some major mathematical problems. So the first example presented here is x plus 6 over x plus 2, and our denominator x plus 2, of course, cannot be equal to 0. So what we do is we take that denominator, set it equal to 0 to find what values of x would be problematic for us, and we would, of course, find that if x equals -2, the denominator would equal to 0. And therefore, we state our domain as x is such that x is not equal to -2, right? X can be any number except -2. So let's take a look at our example below, x plus 6 times x plus 4 over x plus 2 times x plus 4. So now we take this rational and we're going to look at just the denominator, and we see two factors here, x plus 2 and we see x plus 4. And based on the zero product property, we know that in order for this denominator to be equal to 0, either x plus 2 is going to equal 0 or x plus 4 is going to equal 0. So what we'll do is we'll take them and we'll individually solve them. So let's do x plus 2 equal to 0, and we'll also do x plus 4 equal to 0. And now, once we solve this, we're going to get that x equals -2. That's one solution, and x equals -4 as our other solution. So what do these mean now? That means that our domain, if we were stating it, would be listed like this. This is in set notation, of course. So let's make a note. Domain for this rational would be written like this. Brace x is such that x does not equal either of these numbers, so -2 and -4, or -4. And we'll close our set brace right there. So the domain is saying, hey, I know that if I plug in -2 or if I plug in -4, my denominator becomes 0, which means I need to remove those from the domain. Now, some people might mention that these two factors, x plus 4, will cancel each other out, but it's important for us to remember that we cannot cancel them and then take the domain, because that x plus 4 is still going to cause us to divide by 0, even though that factor is going to get canceled out. So just because things cancel does not mean that we can ignore them. We can only do this after checking the domain. Okay? So domain check first, and then you can simplify your expression. And that's exactly what we're going to move into next. So a rational expression written in lowest terms is when the greatest common factor of the numerator and denominator is equal to 1. Basically, anything that is common between the numerator and denominator must get canceled out. They mention here the fundamental theorem of fractions, or the fundamental principle of fractions, and it's essentially just this, that if your fraction has some kind of common factor on the numerator and denominator, we can cancel those two factors out, of course, presuming that the factor wasn't 0, because again, we would have been dividing by 0, right? So they show you this here as AC over BC is equal to A over B, assuming we don't divide by 0, which is the assumption B does not equal 0 and C does not equal 0. So let's look at some examples of how we can simplify a rational. So we'll start with example A here. 2x squared plus 7x minus 4 over 5x squared plus 20x. Now, taking this, what we're going to do is we're going to start by understanding what the factors are, which means we, of course, need to factor this on both top and bottom. So let's rewrite this in its factored form. So take a moment if you want and go ahead and factor these trinomials and that bottom binomial, and let's see what we get. So if you factored this, you should have come to 2x minus 1 and x plus 4 on top. And on the denominator side, we would have had, we can take out 5x as our common factor, and we'd have, of course, had x plus 4. So now you can pretty easily see that on top and bottom there is a common factor. It is x plus 4, and so these would cancel each other out when we simplify. And I would be left with this, 2x minus 1 over 5x. And that would be considered the reduced form, simplified form, or lowest term, however you want to refer to it as, but those are all common ways of stating this. Okay, so we would use a similar approach with part B, or example B, and we would take our 6 minus 3x over x squared minus 4, and we would factor it. So this one's kind of interesting. On the numerator, you can see that the x term is negative and it's been placed second instead of first. If it helps, you can think about this as being negative 3x plus 6, okay? But when I factor this, I'm going to go ahead and take out negative 3, okay? And so when I factor this, I'm going to have this, negative 3 times x minus 2. Okay, and that would give me the same result. And the denominator, guys, is x squared minus 4. Remember, that is a difference of squares, so we would have x plus 2 and x minus 2. So once again, we're seeing some commonality between the top and bottom here. So we'll cross out that x minus 2 and x minus 2. Those will cancel each other out. And we're going to be left with negative 3 over x plus 2. And there we go. We've got this as our lowest terms for both of these examples. So now let's talk about multiplying and dividing these rationals. And you can see kind of the concept is going to be very similar to what we just did in using that fundamental theorem of fractions to reduce rationals. And what we're going to do is we're going to have two rationals that are being multiplied or divided, and we will combine them together and then cancel out any terms that are common or that can be reduced down. Now notice, multiplying and dividing follow some very similar principles in that division actually turns into multiplication. All that they do is flip the second fraction, right? It goes from being c over d to d over c, and it becomes multiplication, right? So remember, that's called taking the reciprocal when you flip that fraction. So keep in mind that division is just the same as multiplication, except you take the second fraction and flip it. Okay, so some examples of multiplication. Now, a few things to point out. One of the things you can do to make your life simpler when you solve these is to simplify as you go. So, for example, in A, 2y squared times 27, and then we've got 9 and 8y to the fifth down here. Okay, so I can try to reduce things across from each other. And what I mean by that is anything that's on top, any term on top can reduce with any term on bottom. So this 2 can actually reduce with this 8 and make it into a 4. 9 and 27, yeah, we can divide 9 out of 27 and make this into a 3 and a 1. Now notice we have two y's here, y squared, and we'll be able to reduce that along with this y to the fifth, making it into a y to the third. So now everything's canceled out in this first term. That's actually going to end up just being a 1. And so I've got 1 times 3 is 3. And on bottom, I've got 1 times 4y to the third. So we've got 4y to the third at the bottom. Okay. Now, if you had multiplied this out the long way, you would still get the same answer. You would just have to reduce your numbers at the end. And it can be a little bit more tedious. So always look for things that we can simplify. Any term on top versus any term on bottom can be simplified. Okay, let's look at problem B now. So example B, you're going to notice that these polynomials in the rational are a little more complex. And what that's going to mean is that we're going to need to factor any of the higher degree polynomials that we see. So that first fraction, the one on the left, you can see that both of those are going to be able to factor. So let's go ahead and take a second and factor those and see if you get this. And here is b factored out. So you can see this is the same exact rational that's given here, and it is just in the factored form. So once you factor each piece and we kind of rewrite it, now we can look for common pieces that will reduce or simplify. So do you already see pieces that will match? Sure, we see 3m plus 4 here on top and on bottom. Those can cancel each other out. We also will see 3m plus 2 on top and bottom. And we can kind of just put together whatever's left, and we should end with m minus 2 over m plus 4. So again, you can't solve this without factoring to see what's common that you can reduce or cancel down. Now, as we move to examples C and D, we're going to see like, hey, these are starting to look a little more complex, but C specifically is different. It has a division symbol. So let's see how we can handle that. So the first thing to do is, why don't we set up C as a multiplication? So go ahead and do that. Remember, we take the second fraction and we flip it. So here I've rewritten the problem, but now stated it as a multiplication. And what you can see is that the second fraction has been flipped to make 24p to the fourth minus 36p cubed over 9p plus 36. Okay, so now that we're at this point, what should our next step be? It should just be to now factor all of the pieces. And for some of these guys, that's just a GCF. So let's go ahead and factor these out. So take a second, pause, and factor these. Okay, so here in yellow, I've now shown you what the factored form looks like. And we can now continue to look for pieces that we can reduce or cancel down. So again, top versus bottom. Any piece on top versus any piece on bottom can simplify. So let's just start with 3p minus 1, canceling these out. Then we can see, oh, there's p plus 4. We can cancel p plus 4 out, top and bottom. And we can also reduce these terms with the coefficients. So I see that we've got p squared and p cubed. So let's go ahead and take these two out from here. And that is going to leave me with a p to the first power. Okay, so let's keep an eye on that, make sure we don't forget that guy. And then let's go ahead and reduce our coefficients, these plain old numbers in the front, out as well. So 12, 9, and 8 definitely have some commonalities, so let's see what we can reduce. 8 and 12 both divide by 4, so we can go ahead and make this into a 3 and reduce our 8 into a 2. Then 3 and 9, 9 can actually reduce to 3 and take this 3 completely out. So on the top, when we put this together now, we'll see that we've got p to the first times 2p minus 3 over 2 times 3, which makes 6. And you could, of course, multiply these coefficients at the bottom together, 8 times 9, and make 72, and then reduce it with the 12 at the top at the end, and you would get the same exact result. But you should get p times 2p minus 3 over 6 as your solution here. Okay, Len, let's now take a second and go through problem D. If you're feeling confident, guys, if you feel like, hey, I have the right ideas in mind, stop and go ahead and try example D on your own, and then check against this answer. Okay, so of course, this one's already multiplying, so we do not need to flip anything, but we're still going to want to factor this so that we can simplify it. So let's take a second and go ahead and factor this down. So here's the first term factored out. On the top, we use the difference of cubes rule, and on the bottom, I use difference of squares. I know that that y squared didn't print properly here, but it should say y squared, which is why we get x plus y and x minus y. Now, on the second bit, you're going to need to use grouping. So just kind of keeping an eye out. Remember, we group these up, and then we're going to factor each piece to see what we can break it down into. And you can see that after factoring, I got 2 plus z times x plus y and 2 plus z times x squared plus y squared in the denominator. Now, note, I just left it as 2 plus z. You could also write it as z plus 2. Those both mean the same thing. More conventionally, z plus 2 would be correct, but I'll fix it at the end if I still have a z plus 2 term. Okay, let's look for some matching pieces. So first thing I see, x minus y and x minus y. Those two will cancel each other out. Then we've also got x plus y here and x plus y at the top on the right. So we can also see the 2 plus z on top and bottom here that we will cancel out. So if we take all of those terms and we cancel them, we are left with x squared plus xy plus y squared in the numerator and x squared plus y squared in the denominator. Now, that does not reduce any further. The top is not factorable, even though it looks like a quadratic. And so we can just box this up and be done. Now we've gone through simplifying and multiplying and dividing rationals, and now let's talk about adding and subtracting them. Now, for fractions to be added together, we know that they need a common denominator. And specifically, we usually rely on what we call the least common denominator, which is basically the most reduced form that we can have common of these two. Okay, so there's a quick reminder there in the green box for you guys. But in general, just remember, we need to make the denominators common, and we do that by multiplying each side by something to get them to match. We always want to use the lowest form of that. That way we don't have to do extra work reducing at the end. So let's look at some examples of adding and subtracting, and we'll just start with example A here, which says 5 over 9x squared plus 1 over 6x. So first thing, we're trying to get the denominators to be common, okay? So first we need to figure out what common multiple can we get of 9 and 6. And we want, of course, the least one so that we don't have to reduce excessively at the end. So 9 and 6 can both become 18. How? Well, I can multiply 9 by 2. So I'm going to do 2 on top and bottom here. And 6 by 3. So we'll do 3 on top and bottom here. Now, we also need to get the variable pieces to match. So notice that I've got x squared here with 9. And so we can get that to match by multiplying an x on the right-hand side as well. So let's see what we get once we have made these denominators common. So 2 times 5 makes 10 over 2 times 9, x squared makes 18 x squared plus 3x over 18x squared. Now that we've got this with common denominators, we can put it together to get our final answer. So 3x plus 10, and I'm just writing it in standard form, so I put it in order, over 18x squared. And we should, of course, reduce if we can at the end. In this case, we cannot, so we will stop right here. And that is the solution to example A. Now let's take a look at example B, which is y over y minus 2 plus 8 over 2 minus y. Now these denominators look a little bit odd because they're so similar, And the only difference is actually that they are negatives of one another, right? So if we multiply either of these by -1, we can get the other denominator instead. So what I'm going to do is I'm going to actually do 2 minus y, and I'm going to multiply that one by -1. And you could absolutely do the other side. The reason I like to multiply this one by -1 is because y minus 2 is in standard form, of course. So once we've done this, we'll leave the left-hand side as y over y minus 2 plus -8 over y minus 2. And now that these denominators are common, let's see what our final answer is. We've got y minus 8 over y minus 2. Now notice, guys, both of these examples, the first and second one, we only add the top, we never add the bottom part. The denominator remains the same once you've gotten it to be consistent, right? Once you have all the denominators matching, that denominator should not change unless you reduce your fraction at the end. Now let's take a look at example C. And example C, you can see, has a lot of different factors at the bottom in the denominators. So we've got x minus 1, x plus 2, minus 1 over x plus 3, and x minus 4. Now this can get a little bit tricky because we're going to need every factor that's on the right to have a matching piece on the left so that the denominators become common. So if we look on the right, I see this x plus 3, but no x plus 3 on the left. So I'm going to multiply an x plus 3 in there. Also x minus 4. And I'm going to need to do that on top and bottom as well. Okay, now what about the right-hand side? Well, the right-hand side now, we're going to say, hey, I don't have an x minus 1 factor. I don't have an x plus 2 factor. So we've got to do that. And again, that's top and bottom. So you can see this is starting to get a little bit inconvenient because of how many terms there are. But overall, we've got something that looks like this. So in blue, you can see I've kind of rewritten the problem again. And all I've done is kind of cleaned up what we had. You can see that both of our denominators are now the same. Even though I haven't bothered to distribute them, they are both, in fact, common now. Okay, so what we can do is we can understand that our denominator is not going to change unless we go reduce at the end. Okay, so now let's see what we can do. On the top, or numerators, these can be simplified. So let's take these down here and simplify them. So if we distribute, we would get something like this. We would have 3 times x squared minus x minus 12 with the same denominator, minus, and then on the right-hand side, we'd have x squared plus x minus 2. Okay, also with the same denominator. And now we can kind of understand that, hey, we know that we're only going to subtract the two pieces on top, right? So we can distribute this 3, and we get 3x squared minus 3x minus 36 minus x squared plus x minus 2. And that negative sign can be distributed into this portion, which means now we get negative x squared, negative x, and plus 2. Now, let's combine our like terms and see what we can get. So we've got 2x squared minus 4x minus 34 over, not forgetting that this was always a fraction, right? So now we're going to bring this denominator that's been common since this point down here. So we've got x minus 1, x plus 2, x plus 3, and x minus 4. And of course, if we wanted to, we could distribute or factor to try and reduce this, but this should be the simplified answer in this case. Okay, Just take caution, guys. If the top piece factors, we should look out for trying to reduce that. You may notice that I didn't write the denominator of the fraction in a couple of these spots right here. And that was just in the interest of saving time and space, because we've understood at this point where I highlighted that the denominators are both the same, and that denominator should remain the same all the way up until our final solution. Okay, now the final group of examples is talking about simplifying complex fractions. And by complex, they just mean fractions that have been nested within other fractions, right? So to simplify these, the easiest approach is usually to cancel out denominators to simplify your fraction into a singular fraction or singular rational so that we can simplify it further from there. So let's take a look at example A. We've got 6 minus 5 over k over 1 plus 5 over k. And what you'll see is that both of these have a denominator of k nested in them. And so what we will do is we can take these denominators and multiply them on top and bottom. Now, since I'm multiplying by k over k, I'm not changing the value of this expression at all, right? So when we distribute this, you should get this is 6 times k, so 6k, and then 5 over k times k is just going to end up being minus 5. And on the bottom, similarly, 1 times k gives us k plus 5k. And for all intents and purposes, this is actually equal to what we started with. We just have to note that, yeah, k does not equal 0. That's just kind of one noteworthy point because this fraction wouldn't be valid in that case. Okay, and now we can take a look at example B, which has a slightly more complex looking denominator for these. So here is B again, a over a plus 1 over a, all over 1 over a plus 1 over a plus 1. Okay, so this time there are actually two denominators that are unique in this. We see the nested a plus 1 denominator, and we see this a denominator. Okay, so the easiest approach is we could take it one denominator at a time. We could take it as all the denominators as one. But let's go ahead and take it with a single one of these at a time. So I'm going to start by multiplying top and bottom by just a. And let's see what we get. So from here on top, a times a over a plus 1 is going to be a squared over a plus 1 plus 1 over a times a is just 1 over a times 1 over a is 1 plus a over a plus 1. So now this portion in red that I've gotten is slightly simpler than what we started with in white. And you can see that some of the fractions have been simplified out. Okay. Now, if we continue this, the denominator that's remaining is a plus 1. So what we'll do is now we can multiply by a plus 1 to top and bottom. So remember, you have to multiply top and bottom. So the first bit, when you multiply, will just give us, and I'm going to go downwards here, a squared plus 1 times a plus 1 is a plus 1. And I'll put parentheses just so it's easy to see that that's where that second piece came from. On bottom, I've got a plus 1 times, or plus a. Okay, and kind of in the simplest form, we've got this. A squared plus a plus 1 over 2a plus 1. And so for that, you can see all I did was I combined the loose-like terms here. So you could have started from the very beginning by multiplying by a times a plus 1 and multiplying both denominators at once to skip a step in this process. However, it can be a little bit messier and sometimes it's a little bit tricky to see, hey, which pieces are going to remain and which ones are not. So you can also take it with this approach where we cancel one denominator at a time. Now let's go ahead and make our note about what should not be equal to 0 in this case, right? So remember, we multiplied by a as a denominator, so a can't be 0, and a plus 1 can't equal 0. And you might rewrite that last one as a does not equal -1 by moving that -1 over, okay? So that is simplifying a complex fraction, or a complex rational, you might say, okay? And all it takes is multiplying by the denominators of the nested fractions. And if you do that, it will simplify out and make your fraction look prettier. I made a note about the restrictions, guys, once again to remind you that those restrictions exist within your domain because in the original expression, a plus 1 was a denominator, a was a denominator. And since we can't divide by 0, it's important that at the end here we say, hey, that a is not 0 and a is not going to be -1 either.